Beneath the Martian dome we dwell, where crimson skies and dreams do tell, a refuge against the void's embrace, humanity's bold, newfound space. One of the biggest questions we have about settling the Red Planet, right after asking if we should or not, is if we should be building domes there or living underground, or even favoring settlements up in space on rotating ring or cylinder habitats. Today I thought we would discuss if we should be building those domes on Mars, and if so, what purposes would they serve, where we should build them, how big, and from what. Needless to say, a transparent dome is unnecessary in some cases, or even counterproductive, for the same reason we don't make transparent roofs on houses. Likewise, some cases require them even when inconvenient or adding a hazard. Though we can also see hybrids, where a skylight in opaque ceilings and windows are used, with blast shutters to handle sudden damage to that transparent glass. But before we get into a summary of the pros and cons of domes, by which we mostly mean transparent or translucent ones, we should note that the classic fear of the dome shattering and sucking everybody out to die in a near vacuum is not a realistic one. Any dome is likely to be made of triangular segments no more than a meter wide, and it would be one of those that shattered. We can build out of much stronger transparent materials than glass these days, and given that diamond can now be economically manufactured and is just carbon, as is graphene, that wonder material of tensile strength, we could potentially be having domes affordably built out of diamond sheets reinforced with thin transparent layers of graphene that would make even modern bulletproof glass look fragile, and certainly would make the roofs of houses and even the armor on lighter military vehicles look soft. But even if you blew out one of those transparent triangles completely, that does not mean everyone suddenly falls over dead or gets sucked out onto the red sands. Air running from a hole into a vacuum only passes through it at a speed similar to the speed of sound at that pressure. Some large dome is going to have several seconds before any significant drop in pressure occurs, and that's enough for some automated pressure switch to pop and let fly a patch, which needn't be more than a compressed gas capsule inside a sturdy inflatable beach ball, which is now going to fly up and wedge into that spot to buy time for a better patch and evacuation. In other words, while there is an unavoidable hazard to any thin-shelled building separating breathable air from a near vacuum, it is a manageable situation. The danger is rather overhyped, and there is a lot of room for plausible technological improvement and innovation. On the flip side, since there's no real water on Mars and gravity is lower, a lot of the downsides of underground facilities go away. They get easier to build and reinforce from low gravity, and they can't flood since there's no water to speak of. Plus, they already provide an inherent radiation shielding and leakage mitigation by their sheer thickness of material around them. So again, we are not discussing an either-or situation, as we'll have both domes and underground facilities, but the individual pros and cons determine if we have tons of domes and just a few underground bunkers, or if domes are like anthills, the tiny surface entrance to a larger complex. Unsurprisingly, both building domes on the surface of Mars and creating underground habitats have their own advantages and challenges, but moreover, the choice between these two options would depend on factors like the goals of the colonization effort, the available technology, and the specific conditions on Mars, which vary by where you are on Mars, and of course dome technology being used on other planets based off Martian designs will need to adapt to, where they have different air composition, gravity, and pressure. Some designs are very different. For instance, if the planet you're on has a thicker atmosphere than you want, rather than not enough air. So what are the main advantages of domes on Mars? First, natural light. Domes would allow natural sunlight to reach the interior, which is crucial for maintaining human health and well-being. We're only now beginning to appreciate how critical the right type, spectrum, and duration of light are to normal human rhythms, same for animals and plants, and since Mars is basically the only planet with an even vaguely Earth-like day, it makes sense to take advantage of that over purely artificial lighting. That day is close to Earth's and off in a good way, I'd say. It's a little over half an hour longer, so a little extra sleep each day. Second is agriculture and botany. Controlled environments within domes could potentially support plant growth, just as well as artificial lighting underground, and without a lot of extra power needs and equipment. Third, solar power. Domes could incorporate solar panels on their surfaces or under their surface to generate electricity, and you could get some effort saved since you can clean them as a package, or if they are under a dome, don't need to put a spacesuit on to go to tend to them. Fourth, human nature. One might be the toughest duster there is, who enjoys wearing their second skin kind of isolated suit for weeks, but it still makes sense to do things like sports without it, for if your second skin is impenetrable, your bones are still human. You can do sports underground for sure, but a wide open space like a park offers a much more interesting degree of freedom than a gym room. Besides, a jazz party under the starry sky might seem like a distraction for a scientific expedition, but might as well be vital for survival of a permanent local community. If we want to settle Mars, we have to do it with people, and they have a lot of less tangible needs. And the last big one, fifth, visibility. Surface structures could provide a view of the Martian landscape, aiding in research and exploration. You can go sit in a domed garden area, working on supplementing your food for a base or settlement, and still enjoy the Martian landscape and night sky. So those are the big five typically brought up in favor of domes, with the possible sixth that if you do fully terraform Mars one day, peeling out the domes to enjoy the open sky, or just converting the existing ones to agricultural greenhouses or parks would seem easier. How about challenges? First, we've got radiation. Mars lacks a substantial atmosphere and magnetic field, exposing its surface to higher levels of cosmic and solar radiation. Domes would need to be designed to provide radiation protection, and one of our big problems with a lot of our transparent materials is they tend to take a lot of wear and tear from ultraviolet light, which is also less filtered out by the thinner Martian atmosphere than on Earth. Second, we've got micrometeoroids. Same as with radiation, the thin atmosphere offers less protection from micrometeoroid impacts, so dome materials would need to be resilient, though the protection is not zero like on an airless planet, and since most micrometeors are very tiny, even the thin Martian atmosphere does help a lot. Also, as we noted a bit ago, we already have much sturdier, economically viable alternatives to glass, and some on the radar might rival battleship armor. Third is the wider temperature range. Surface temperatures on Mars are much colder than Earth on average, so we need to heat a dome environment and give it good insulation. Also, while colder overall, the Martian temperature can vary widely, from extremely cold to relatively warm, and over a short period of time. So you're getting extreme variation like you'd expect in a desert, only more so. As a result, domes would need effective insulation and temperature regulation systems, and this only adds to our fourth challenge with domes, which is the maintenance needs. Surface structures would be exposed to the harsh Martian environment like dust and radiation, potentially requiring constant cleaning, maintenance, and repairs. There is a good chance a robot could handle a lot of the exterior cleaning and polishing though, a Roomba for Mars rather than needing to suit up and go out to wipe off the dust and polish out scratches, and which would probably be able to do double duty with cleaning solar panels. I should also add that while domes are attractive for letting us see the sky and get some sun, they also would have certain psychological burdens for folks worrying it might be damaged and that only a thin dome protects them. When you're already 100 million miles from home on a planet with very few people and resources for handling problems, every little bit of extra stress and psychological burden is worthy of note and to be avoided where practical. So that's the major pros and cons of domes. How does that contrast to building underground habitats? First, we have an easier time digging a hole than using local regolith as shielding when we're not needing clear and precisely engineered dome panels. As such, ISRU, or in-situ resource utilization, is way easier with underground facilities, assuming you even can practically make your transport materials for domes on Mars rather than shipping them in from Earth, or perhaps the Moon. This is a very big factor, as even if domes have net advantages, if you need to spend a few $billions to bring the material in from Earth, that's probably not going to result in any more domes than is absolutely necessary. Second is shielding, as the Martian soil and rock would provide natural radiation shielding and micrometeor protection, enhancing the safety of underground habitats. This is also a good reminder that a dome does not have to be transparent. We could dig out some tunnels and use that regolith to form a lot of walls for structures on the surface, including covering inflated structures over with regolith. The third advantage of underground or even thick rock domes is temperature stability. The sheer thermal mass protects against extreme cold and heat on the surface. This contributes to our fourth advantage of energy efficiency, as underground habitats would require much less energy for heating and cooling due to the insulating properties of the Martian regolith. The fifth is the cost of maintenance. Building a dome might be costly, but keeping it clean and shiny is a constant expenditure. There are some challenges though, beginning with needing equipment to dig with, and the reality is that machines and equipment for digging through rock and regolith tend to be inherently thick and heavy, and mass is not your friend if you're a space traveler. We would also need a lot of field testing of designs built for a vacuum or low pressure environment for anything more complex than a shovel or a pickaxe, though we might have prototypes for use on the moon before this. And again, this is one of the many reasons I strongly favor a focus on a moon base before a crewed mission to Mars. And as with there, if you've got a ground-penetrating radar, you can find spots that are craters filled with dust that would be easier to scrape out. I would tend to guess that better and more automated drilling technology for making tunnels is something whose value on Earth will be great enough to see a lot of this technology get improved on here in the next couple decades. If you have a robot that can dig you a utility tunnel, you've got yourself a multi-billion-dollar invention. Second, you must provide artificial lighting inside the tunnels anyway, which necessitates solar panels on the surface needing maintenance and cleaning unless you have a nuclear reactor. If you want to grow food on Mars, you need light, and sunlight would tend to seem easier. The other big one is the psychological impact. Living underground for extended periods could be brutal for astronauts and early settlers already enduring the stress of living on a distant and hostile planet. Moreover, the psychological effects on inhabitants due to lack of natural light and open views might simply make this option impossible. Needless to say, a combination of both approaches might be the most practical solution. Surface domes could serve as greenhouses, entrances, and recreational spaces, while underground habitats could provide the primary living quarters or sleeping quarters, and offer radiation protection and easier climate control for storage facilities. And again, you have a lot of in-betweens. Much as the windows on your house provide a lot of lighting even if it's only a tiny fraction of the sunlight pounding off your roof, an underground section or regolith-covered dome could have skylights. You can do windows too, as that lower gravity means you could put a big stone slab overhead and leave the sides open with recessed windows, and bounce light in off of mirrors around the hab. These can be manufactured from durable local metal so as to be easily polished back to a shine if a dust storm roughs them up, and get you plenty of light while still giving you good insulation, radiation shielding, and micrometeor protection. This works even better on the moon and other lower gravity spots since you can heap tons of rock on top of your roof and not only not need much structure to support that, but can rely on the internal air pressure to carry some of that load. Again though, I don't want to imply you have to rely on regolith for your protection. You can have a blast shutter ready to pop on a pressure switch or command to slam shut over a window, or even a whole dome. They don't need as much help swinging up in low gravity, but you also don't need to make them super thick, as you could have ground up regolith ready to spray in between the shutter and damaged glass, or even just pumped in water to freeze as protective ice. Something like that might be standard operating procedure for protecting a dome too. Some inflatable bags blow over on top of it, and then your water reserves get tapped to pump a thin layer of water to freeze over the dome, and you melt it to reclaim most of your water after the dust storm or attack or whichever has passed. As mentioned, we also have options for plugging gaps quickly. That inflatable beach ball patch is one, a drone shaped like a glass panel is another, and doubtless many others that experience will prompt from innovative minds. And I think that means we can contemplate more fragile materials too, so let's move on to what we can build them out of. We can send materials like polycarbonate to Mars on a ship, but that's not likely to be viable beyond the first few missions with minimal domes involved. On the extreme end, as I mentioned earlier, we do have a lot of carbon on Mars, and that's what both diamond and graphene are exclusively made from. Indeed, you could suck in the local air, 95% carbon dioxide and 3% nitrogen, with most of the rest being argon, and sequester that carbon from the carbon dioxide as diamond and graphene, and use the leftover oxygen and nitrogen for breathing and for plants in those domes. There's not enough nitrogen on Mars for terraforming efforts, but relatively low-height domes need far less air and nitrogen in that air. You might need to still bring in comets for all the nitrogen you would need for doming over an entire Martian surface, what we call paraterraforming or building a ward house, a planet-sized greenhouse, but otherwise you have plenty of nitrogen for those domes from the air present. Though thin as it is, other nitrogen sources on Mars would be preferable if available. Diamond domes and ward houses are in that further future zone, more beyond the scope of what we are discussing today, the realm where we wonder if we should build orbital space habitats around Mars instead, or be erecting vast space mirrors to warm the planet and orbital solar power arrays to run enormous electromagnets to create an artificial magnetosphere. See our episodes Springtime on Mars or Making a Magnetosphere for Mars for more details on such projects. Closer to the now, we have the option of using local regolith to make glass, which is plentiful in the silicon dioxide that glass is made of, along with other substances like ruby or sapphire, which themselves are only a little bit softer than diamond, as a reminder that transparent does not mean weak and that diamond is not the exception to the rule. Solar kilns and ovens are probably your best bet, and here the thin atmosphere helps us as we can more easily insulate it in a near vacuum environment, making heating, baking, and melting local regolith a bit easier. Nuclear power is also good for this, maybe better for running an arc furnace, and in both cases running such production is a good use of the surplus power that you need to have available for safety's sake, or as an inherent byproduct of having solar panels out at noon that are big enough to still power the place when it's less sunny in morning or evening. At noon, you run your energy-intensive industries. Basalt fiber or regular fiberglass should be manufacturable on Mars too, and basalt fiber is sturdier and a decent insulator. We don't want to rule out locally manufactured acrylic glass or polycarbonate too, though that feels like a heavier lift, even if they are materials that are often better to work with. When I built my own greenhouse here on my farm, I used polycarbonate and definitely preferred working with that over glass. That said, I probably would have saved net time and energy by just throwing new plastic sheeting over it every year, and it is a reminder that giant inflatable structures are doable, and you could probably have multiple layers and removable segments so that worn down pieces could be brought in for recycling. This is why I tend to think early structures on Mars will lean heavily on inflatables. They don't need to last forever or look pretty, and if you need the aesthetic, you can have a lot of cool and meaningful patches. You can bring along a giant heavy kiln for making glass, or a framework you might fill with ground regolith for the massive insulation. Or you could bring along a small test one which also produced oxygen from melting rock that your astronaut could breathe and use for inflating structures and keeping up with leakage. Indeed, a decent leak helps to ensure you don't need a carbon dioxide scrubber as long as you just keep making new oxygen. Early on, we would have different parameters for what is okay than when we're building permanent bases for 100 people, let alone in mid-settlement phase with tens of thousands of people living there. Though leakage might still be considered fine for them too. As we've mentioned before, the only thing Mars lacks abundantly to be decently Earth-like, besides gravity, is nitrogen and hydrogen for air and water. The oxygen for both those is in plentiful supply, so blowing megatons of it out of your sprawling dome cities every year might be considered free terraforming as it slowly accumulates in the Martian environment. As a reminder, since inflatable structures make people think of wind blowing them over, while the wind can get fast on Mars and carry a lot of dust, the air is so thin that you could be standing in hurricane-speed winds and barely feel shoved on. It's not the speed that matters, it's the momentum transfer, and a handful of high-speed particles doesn't shove you as much as a bunch of slower-speed particles on Earth will. We can't ignore wind altogether in our designs like we can when contemplating ultra-tall towers on the airless and lower-gravity moon, but is a minimal factor and doesn't limit the use of thin and light materials or inflatable ones. Nonetheless, it is hard to imagine we would keep inflatables as time goes on, with the caveat they would likely have a role for travelers. If you're the captain of an ice hauler bringing giant blocks of ice down to an emerging dome city, it is very likely you have an elaborate inflatable shelter, possibly inflatable solar panels too, so you can get out of your cargo truck and spacesuit during your journey of a few thousand miles over terrain with no roads or gas stations. In that same way, you might have charging stations along the way that had big batteries and panels and inflatable habitats when convoys arrived. Would we expand more underground or above ground? That depends. It might turn out we really don't adapt well to 24.5-hour days and need to be underground for Earth-length artificial lighting. Or it may turn out Martian gravity isn't enough for healthy humans in the long term, in which case you might see bedrooms or living quarters in big underground centrifuges with sloped floors to combine Martian and spin gravity. You might do that for a whole dome too, spin it and everything inside it and give it a sloped floor, sometimes called a roto city or bull habitat, and the lower the gravity and higher total gravity you want, the more steeply sloped that floor needs to be. There's no real maximum size on domes, especially with less air and gravity shoving on your structure, but this would be one reason why you don't see kilometer tall and wide ones, or ones that look like bubble wrap with every single room being its own dome or structure, in favor of relatively large domes but not truly enormous ones. The nature of spin gravity is that the bigger you go, the more even and natural the spin gravity is, but the faster it needs to turn, which could get tricky in an environment with lots of rock nearby and at least some air in the native environment causing drag. And that size is likely to be under a kilometer wide and more than a couple hundred meters, both well inside practical engineering sizes for a dome, though you could get a diameter of nearly 20 kilometers with a structure spinning at just less than the speed of sound on Mars and only seeking to produce 2/3 normal gravity by spin to combine for full 1G Earth gravity with existing Martian gravity. This is a big enough dome that you would have significantly lower pressure at the top from sheer altitude, even though it's a pressurized vessel, and to have its own weather. Though you'll get some of that in the smaller domes too. The Goodyear blimp hangar here in northeast Ohio was known for being so large it rained inside it sometimes. Factors like that, which we can't really predict yet, are also likely to control dome size. Of course, if you did want to avoid any drag issues on bigger spinning domes, you could use other tricks for rotating habitats in space of having a rotating structure inside a slightly larger non-rotating sheath with a vacuum that it can roll around in stably and friction-free. Another backup dome, and one that if both got punctured, is spinning so that hole in the outer layer is not in the same place as the hole in the internal spinning layer. When we go beyond a few thousand people, we need to stop thinking of micrometeors and start thinking of accidents, malice, or warfare as causes of punctures in a dome. Would we see domes eventually sprawl all over Mars? I think so, and honestly I would not be surprised if even nascent oceans were domed over and switched to floating sea domes later on. For one thing, low gravity affects architecture. We don't build too tall for normal homes away from denser parts of cities because height and gravity and wind make that structure need to be tougher and more expensive to build and leave you with a home you need to walk up and down a lot of steps for. When gravity is 2/5 normal, steps are a lot easier and the danger of falling down those stairs and being seriously injured is a lot lower. So a house might have a big dome or collection of interlocking domes over the house or property. Those outer domes might be thinner and cheaper types because a drone that can race out and shove a breathing mask onto your face, spray your skin with vacuum-protected foam, and drag you back to safety might be cheaper than building super sturdy and safe domes on your property, especially since you probably want that drone anyway. Some dome spaces are like a greenhouse, others more like a living room or workspace with a clear ceiling. You probably have a lot of fans going to move the air around too. Under those domes you have skylights set just above the ground level to more living areas, and since they're in the ceiling it's generally going to feel a lot brighter than a room with similarly sized windows, so very comfortable even given the reduced sunshine on Mars from being further from the sun. This can also still be garden and hydroponic space. Lower levels are sleeping rooms or less used spaces, nicely insulated from light and sound, and storage rooms below those, water cisterns and reserve air tanks, and maybe tunnels to neighboring dome habitats. After all, it's a little harder to make safe walkways unless you're building tunnels or dome tunnels the whole way. On the flip side, you can do amazing railroads in low-pressure environments with pressurized cars. You can do domes inside domes too, so the big cheap dome might have others underneath it, and Mars is just cold, so we either have to build millions of square kilometers of reflective mirrors in space to add sunlight, or we build domes over everything to keep the heat in, maybe both. Here's the key thing though, with domes you get control over your local environment. If your neighbor is burning trash or the factory down the road is spewing out smog, you have a barrier. You add lots of passages with remote operation to let things like pollinators or birds move through, so they need not each be independent ecosystems, and yet they offer far more efficiency and options to people. so I don't think many domes on Mars would be removed even if they had an atmosphere terraformed in, and indeed I could imagine that trend coming home to Earth, to see domes get used here more, especially in tundra towns and desert domains. Ultimately, while I fully expect humanity's future on Mars to be a grand and varied one, that the Red Planet will be home to a billion different stories, I think most of those stories will be told under the domes of Mars. So we have some announcements and channel news coming up, but speaking of news, I'm sure you've noticed that the news often doesn't seem focused on giving you a full and grounded view on any event or issue, but the reporter's personal opinions or their outlet's ideology. I'm glad to say coverage of science still tends to be low on partisanship compared to most topics, but even here we see it, particularly in polarizing examples like articles on Elon Musk. And since he's so involved with topics like Mars, our topic for today, we have to worry that any report on Mars might be skewed by the reporter's views on Musk. As we see in comparisons of the same headlines, left-leaning outlets focused on a clash between Sunak and Musk, while the right focused on Musk's warning about AI capabilities. Ideally, it would be nice if news didn't have biases in coverage, but in the absence of that, it's nice to know what those biases are, and that's where Ground News can help. Ground News is a website and app designed to help you pull back the curtain on media bias. Every story comes with a quick visual breakdown of the political bias, factuality, and ownership of the source's reporting, all backed by ratings from 3 independent news monitoring organizations. Ground News is a platform that makes it easy to swipe between headlines to discover what details are emphasized, exaggerated, or left out entirely, and you can't even see your own news bias preferences, so you don't live in an echo chamber. I particularly like their blind spot feature, which shows what stories are being covered by one group while ignored or swept under the rug by another. Ground News is a fantastic tool for sifting through daily misinformation and bias. They provide all the tools you need to be a critical thinker, and I cannot recommend it enough. In fact, I believe Ground News is so useful that I'm offering 30% off their Vantage subscription. You can only access this discount through my link, so go to ground.news/IsaacArthur or click the link in the video description and support an independent news platform working to make the media landscape more transparent. So before we get to our schedule, I want to remind everyone that the National Space Society's Space Policy Debates program is calling on high school and university students around the world to debate the hottest topics in space exploration, utilization, settlement, and governance. If you enjoy debate and are a student or a teacher interested in mentoring them and want to dive into the cosmos and shape the future, you can join this electrifying journey at the Spun Debates. I'll link the details in the episode description. Also, the New World Space Conference is coming up on November 17th and 18th, 2023 at Bullock, Texas State Museum in Austin, Texas, along with their Space Cowboy Ball. So if you live in the area, grab some tickets and check it out. Next week, we'll examine the astronomy of double planets, where the big object in the sky isn't a moon, but a much larger and bluer and greener planet, and ask if life might be able to arise on such worlds and migrate between them. Then our monthly livestream Q&A is cancelled this month, but we will still be having a short episode that day on space hygiene, before closing the month out on November 30th with Agri-Worlds, and a discussion of how you could farm an entire planet. Then we'll start December off on the 7th with a discussion of how to select crews for spaceships. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.